everyone. We're gonna learn 6.2 line integrals. Okay, so we have a learning objective here. Okay, so what is the line integrals? So integrals integrate to integrate multi-variables function and vector fields over arbitrary curves in a plane or in space. Yeah, so we have two types of line integrals. One is the scalar line integrals and vector line integrals, right? So scalar function, we talked last section, right? So scalar function is about the temperature, cost, height, etc. This is for physics, right? Most of the time physics, the subject. So scalar line integral, so we have integral plus curve. So not the straight line, okay? So it's a curve in a plane or space. So we called this is also curve integrals, all right? Now, vector line integrals, like a vector, right? So integral plus curve through vector field, all right? So let's take a look. So we have a picture, line, right? Curve, yes? Okay, now we have the f with function, which is a scalar function, right? All right, now we have a smooth curve, C. So we're using just the first letter C, right? And that is a parameterized, parameterized by this vector equation, right? Okay, now we have a integral along C curve, right? This is a curve. Now we have a Riemann sum again, right? Riemann sum. So limit n approach to positive infinity, sum of f of p stars as asterisk there, and then delta s sub I, right? So we have that. And then we have another one. So this is for 3-dimension, this is for 2-dimension, right? Okay, so let's do this one. So find the value of integral of, we have integral of C curve 2. Okay, let's take a look. We have this one like a function, right? Function f of x, y means the height, right? Z. Yeah. So in that case, we have z, that means xy plane. They said where the curve C is upper half of the unit circle. Yeah. Okay. So let's take a look at the picture here. Yeah. So this C is upper half of a unit circle. Yeah. So it's not the whole like that, right? Okay. Now we want to know about the area of rectangle. Because if we make it's hard to see, right? So if we make this upper unit circle, make a flat, that is a rectangle, right? We know that, right? So if we make area of rectangle, length times width, which is we can say that height times width, either way, right? So we can make that. Then height in the case is 2, right? So this is 2. Height 2, right? Because z equal to 2, right? Or f of x, y equal to 2, right? Okay, then what's the width? So this is width, This is indicate width, right? This is width. All right, then the width is upper unit circle. Then think about this. Look, so x is positive and come back to the negative, right? So if we think about upper unit circle, right? So x-axis, y-axis, then 0 to pi, right? So there is pi, 0. Yeah, that's how we get 2 pi. Make sense? Yeah. Okay, so how about we using like earlier definition, make R of t be parameterization of the curve C. Okay, let's take a look. So we have, can you see? Okay, let me make it bigger. So when we make a parameterize, then we have, so basically we make a t, right? So think about that, right? Okay, so then we have a vector field x over t, y over t, z over t, right? All right, then we have f of, we substitute r over t, right? Then this is a 2 because we have a constant function, right? Okay, now by definition, integral of the curve and f ds, then we're using Riemann sum. In that case, we have f of r over t and delta s sub I, right? All right, then we know this is a 2 constant function, right? Okay, now what is summation of delta s? That is all the distance, the add up all the distance. That means the length of a curve, which is pi. Make sense? Okay, let's take a look, theorem 6.3. Okay, so if we do Riemann sum, always very difficult, right? It's a lot of work. So we make life easier. So what we do, we just using formula, right? So how do you do? So if we have line integral, then we are using from A to B. Then, like earlier question, we make a parameterization. So f of r over t and magnitude of derivative of r over t. And then they change that dt, right? Can you see that from ds? All right. Then we have an experience, right? From the chapter 3. What is this? This is same as the individual x prime over t plus y prime over t and then g prime over t, right? And then we have a magnitude, which is square each of them, right? So let's take a look this one too. Da-da-da. Okay, so if we have a 2-dimension, we are using this. Yeah, if we have a 3-dimension, we are using this. Yeah, so just to this one is the same as that, right? We had the experience before. Okay. Now one more note. So if we have f of x, y, z equal to 1, then we can express this one here, right? So line integral 1 ds, since 1, right? So we can just express line integral of ds, right? Then that will be length of curve C. Yeah. So like earlier we had the experience, right? So just ds. What's just ds? Yeah. There is the length of a curve, right? Same as here. Yeah. Means that add all the tiny pieces of distance along the curve, that is the total length of the curve. Yeah. Okay. Now, let's do this example. All right, so find the value of integral of, this is the function ds, where the curve is part of helix, parameterized by r over t equal to cosine t, sine t, t is between 0 and 2 pi. Yeah, okay. Let's see using the formula. So I wrote down the formula here. Okay. All right. Now, okay. So let's do. We have start with the line integral x squared plus y squared plus z, not the square. Yes, right? Okay, equal to, we're gonna make a parameterize. So we are going to make the limit from 0 to 2 pi, 0 to 2 pi. And then x squared, so let's make x cosine t, sine t as y, z equal to t, right? So x squared, which is cosine square t, plus y squared, which is sine square t, plus z, which is t. Yeah? Okay. Now we have to have what is the magnitude of r prime over t, right? Okay. So magnitude of r prime over t will be square root of x prime over t. So what is x prime over t? What's the derivative of cosine? Negative sine, right? And then square them, plus y prime over t. So derivative of sine, which is cosine t squared. And then derivative of t, which is 1 square, right? Okay, now this is 1, right? So 1 plus 1, we have a square root of 2. Yeah? All right. Okay, let's take a look here too. Here is as well 1, right? All right. So then we will get square root of 2, bring outside of integral. So that will be square root of 2. From 0 to 2 pi, we have 1 plus t dt. Sorry, I did not change the dt, right? We have to have that. All right. Now, square root of 2 So we want to integrate term by term. So first term we have t. Second term we have t squared over 2. And then we want to evaluate from 0 to 2 pi, right? Okay. So there will be square root of 2 pi plus 2 pi square plus 2. And then the other one is 0. Okay. Can you please calculate? Did you get the 36.8? Okay. Good job. Okay, so we have a wire has a shape that can be modeled with a parameterization. And we have r of t is cosine t sine t 2/3 of t to the 3 over 2 power, and t is between 0 and 4 pi. Find the length of wire. Okay, so let's start with integral of 1 ds. There will be length of wire. Start with that. So that is given. And then we want to make a parameter right, right? So let's do this one. This is length of okay. Then ds. So ds, we have this one, right? From previous definition. Okay. Now, we have t is between 0 to 4 pi. 0 to 4 pi. And then magnitude of the derivative of each, right? So let's do that. Magnitude, so we make a square down, square root of, and derivative of cosine t, negative sine t squared plus derivative of sine t, which is cosine t squared. Now, derivative of 2/3 of t to the 3 over 2 power. So we drop the power, then cancel out, right? And reduce by 1. So let's make it here. This looks weird. Let me see. Better? Eh. Yeah. Okay. Note. Derivative. So we have 2/3 3 over 2. And we have t to the reduced by 1, 2 over 2, so 1/2, right? 1/2. Okay. Then there will be plus square root of t, and then square them, right? Okay. So we knew this is equal to 1. And then we get 1 plus t. We had the experience earlier, right? 1 plus t. Okay. Now, dt. Okay, we want to integrate. So that will be 0 to 4 pi, and then from 0 to 4 pi, that is 1/2, right? So 1 plus t to the 1/2 dt. Then integrate. So add 2 over 2. So 3 over 2, 2/3. 1 plus t to the 3 over 2, right? And then we want to evaluate from 0 to 4 pi. So that will be 2/3 and 1 plus 4 pi 3 over 2 and minus 1 to the 3 over 2, right? So there is a 1. Can you please calculate? So do you get approximately 32.645? Good job. Okay, so let's take a look vector line integral here. So we have arc length. Okay, so F we consider like a vector field. Then we have a T, so tangent vector again, right? We have a P each point. All right, so we have a W, which is work done. So we call the work done by field. So integral over the line curve. So we have F, vector field, and there is a dot product involved. And then T as a tangent vector, we have a ds. Yeah, ds we had earlier, which is arc length, which is tiny steps of uh, distance, right? So we had experienced the ds equal to magnitude of r prime over t dt, right? Okay, now definition saying integral over C and vector field dot product of tangent vector ds. Yeah, and then we are using Riemann sum, and then we have a expression there, right? Okay, now let me start with that formula. So we have integral over curve and then line integral. Yeah, so vector field as dot product with tangent vector ds. Yeah, so tangent vector, we can express that I have here. So r prime of t over magnitude of r prime of t, right? Okay, now we want to make a parameterized of the vector field. So we can express this one like f of r over t, right? Okay, tangent vector, this one. So dot product with r prime over t over magnitude of r prime over t. Okay, now ds we can express it this way, right? So that will be magnitude of r prime over t dt. Yeah. Okay, now we can simplify. So simplify like that. Then we will have, so integral, line integral, vector field of r over t, parameterized, and dot product with r prime over t, yeah, dt at the end, right? Okay, so this one we can express as line integral, the vector field dot product with dr. Yeah. So we can make a corresponding this one as that. This one is this. Yeah. Okay. Or I can express this way, right? Note r prime over t. I'm sorry, r prime over t equal to x over t, y over t. Can I say z over t? Then dr equal to x prime over t, y prime over t, right? Z prime over t, which is r prime over t, right? Yeah, we can express this way. Yeah. Okay, let's do this problem. Okay, so let's find this problem, find the value of line integral of f dot product of dr, right? Okay, so where C is the semicircle, r over t equal to cosine t sine t, and t is between 0 and pi, and the vector field is negative y and x. Okay, so we knew that, we just found out what is this means, right? So line integral of parameterized, and then dr means r prime over t dt, right? Okay, now let's take a look the vector field. Negative y, x means y in the case sign. So there will be, keep the negative there, sine t, x will be cosine t, right? Okay, let's do that. Then there will be line integral, and then f of r over t, which is this, yeah? So there will be negative sine t cosine t. Okay, now what is the derivative of the t? Negative sine t, derivative of sine, which is cosine, right? So we will have negative sine t cosine t dt, right? It's a dot product. So there will be sine square t, yeah? We multiply component with the first component with the first component, and then we add second component with the second component, right? It's the dot product. So plus cosine square t dt, right? Okay, we knew this is 1. So there will be line integral 1 dt. Oh, I did not make a, after parameterize, we have to make a evaluation, the limit, right? Okay, between 0 to pi, 0 to pi, 0 to pi, 0 to pi. All right, so we do integrate. We have a t, we want to evaluate from 0 to pi, so it will be pi. Yeah, very good. Okay, so here is some note here. So let's see the oriented curve. So oriented curve means they go to some direction, right? And negative C denote the same curve, but with the orientation reversed. So basically going this direction, but reverse, going another other direction. There will be orientation reversed. All right. Then we have a negative sign there. Okay, so let's do this one. It's very similar with a previous example, but we have a cosine t plus pi, and then same vector field. Okay, this means the negative y, negative sine t, and x equal to cosine t plus pi, right? So let's do this. Integral, line integral, the vector field, and dot product with dr, right? Okay, so there will be line integral of the parameterized with r over t and dot product with r prime over t dt. Yeah. Okay. So that will be, we change that, then limit will be 0 to pi, same as earlier. And then there is negative sine t cosine t plus pi. And dot product with, what's the derivative of cosine t plus pi? Negative sign, yeah? Negative sign. Oh my gosh. Okay. Negative sine t plus pi. And what's the derivative of a sine? It's cosine t, yeah? Okay, dot product. The first one, oh, we have a special, huh? Okay, so let's make a special one. Note. Sine alpha plus beta equal to sine alpha cosine beta plus cosine alpha sine beta, yeah? We have cosine alpha plus beta and cosh, so cosine alpha cosine beta plus negative sine alpha sine beta. Yeah. Okay. Then cosine t plus pi. So let's work. So cosine t plus pi, follow the formula. Cosine t cosine pi minus sine t sine pi. Yeah. Okay. Sine pi equal to 0. This is 0. So we have cosine pi equal to 1, right? Actually, negative 1. So we get negative cosine t. How about sine t plus pi? Follow the formula sine alpha sine t cosine beta t, pi plus cosine t sine pi. Yeah. Okay, which one is 0? Sine pi is 0 as well. And cosine pi is 1. So we have a sine t then. Yeah. Oh, negative 1. Keep forget. Negative 1. Yes. Negative 1. So this one also negative sine t. Okay. Now let's write down there will be from 0 to pi, negative sine t, cosine t plus pi, negative cosine t, dot product, negative sine t, cosine t. Yes? It's hard to see? Yeah. Better? Okay. Now we multiply. So first component with the first component is sine square t. Second with the second. But it's negative, yeah? Negative cosine square t dt. Okay, we want to make a positive one, right? So maybe we take out, factor out with a negative sign. Wait a minute. Did I make a mistake? Hold on 1 second. Let me check that. Okay, I found where I make a mistake. So we have negative sine t plus pi, but then I did sine t plus pi, which is negative sine t. Then there is negative, negative, which is a positive, right? So this will be positive. Then there will be negative. Negative. Yeah, then we can factor out with a negative sign. So there will be 0 to pi negative factor out sine square t plus cosine square t dt, right? Now we knew this is 1. So then we had the experience earlier from 0 to pi negative 1 dt. So there will be negative t from 0 to pi. So there will be negative pi. Yeah. Okay. So this is negative pi, means that the reverse oriented, right? Reverse orientation. Reversed. Okay, so this means the orientation of the curve goes against the flow of the vector field. Makes sense, yeah? Yeah, so means that if direction goes this way, then goes the opposite from the flow. Yeah, very good. All right, so we have another terminology, flux. So flux of a vector field F across the C, line integral gives this formula. Okay, so what is the flux means? Flux means how much of a vector field flows through a curve. Okay, all right, so we have this formula. This is from the unit normal vector. We did it before, right? Okay, in that case, normal vector gives us that y prime over t and negative x prime over t. All right, so this is the picture of the vector fields And this is a curve. This is a curve. And then normal vector is perpendicular with the curve. We know that, right? Yeah. Okay. Now, this formula becomes like that. Yeah. So, n as a unit normal vector, like we had earlier, tangent vector, right? There's also unit tangent vector, right? So unit normal vector. Then we can express this formula, the vector field, and then the parameterize and dot product with the normal vector of t dt. Yeah? Okay. Why? Because let's start with this. Curve C, the vector field and normal vector, unit normal vector ds. Yeah? Okay, so there will be curve, the vector field, and the unit normal vector, we can express n over t over magnitude of n over t ds. Yeah? Okay. We know what's ds, right? So magnitude of r prime over t and t ds is r prime over t, right? Uh, okay, now we had note n over t. I mentioned earlier y prime over t and minus x prime over t, right? Okay, then we take the magnitude. So that will be f n over t over magnitude. So that will be square root of y prime over t squared plus negative x prime over t squared, right? And we have magnitude of r prime over t, right? Okay, so negative x prime over t, we make a square there. It's x prime over t squared, right? Then this is the same as magnitude of r prime over t, same, right? So we can simplify. Then there will be uh, we have to change the parameterize because we were using that, right? Since when? When we do ds, change it to ds, yeah? Parameterize. Since here, we change it. Maybe maybe, and then vector field parameterization and dot product with the normal vector. Yeah, okay. That's how we got the formula. Okay, so this is this this is the last question. Calculate The flux of the vector field is 2x, 2y across a unit circle oriented counterclockwise, right? So this is the picture. We have a vector field and then counterclockwise, right? Okay, so let's make a parameter parameterization, okay, of unit circle. So let me write down note. Note parameterization of unit circle. Okay, so we make all of t equal to cosine t, sine t. T is between 0 to 2 pi. Yeah? Okay. Now, the formula, right? So we have to have use that. So start with, right? Okay. Now, the vector field is 2x, 2y, right? 2x and 2y. Then x indicates cosine t, y indicates sine t. So the vector field with the parameterized, which is 2 cosine t and 2 sine t, right? From 0 to 2 pi, we have 2 cosine t, 2 sine t. Okay, so normal curve, we have what? So we have y prime over t, y prime, correct, right? Plus minus x prime over t. Yeah. So we have y prime, which is cosine t, and x prime over t, which is negative sine t, but we have a negative, so it's positive sine t. Yeah? Wait a minute. Must be have comma, right? Yeah. So this negative sign, it's not the subtraction, it's negative. Made a mistake. Negative sign in front of x prime t, right? Okay, so that will be, what did I say? Cosine t and sine t. Yeah? dt. Okay, dot product we have. So first component with the first component. So there will be 2 cosine square t plus second component with the second component 2 sine square t. Yeah. Okay. dt. And let's factor out 2 from 0 to 2 pi cosine square t plus sine square t dt, which is 1. Okay, then there will be, let's integrate. So 2t from 0 to 2 pi, which is 4 pi. Yeah. All right. Thank you for watching. I'll see you next video. Thank you very much. Bye.